Alright, you guys, so what we have are two more cases of oblique triangles. So the law of sines actually handles case 1 and case 2, but we need a new law of cosines is what it will be, to handle case 3 and 4. Again, case 3 is when we have a side angle side. So again, if I have a side and a side, and then I know that angle. So something of that nature, and it could have been anywhere, right? It could have been on, side, and then I know that angle, or I know that angle. So it doesn't really matter where, but I know side, and then the angle in between them. And then, of course, the last one is when I know all the sides. Okay, so it turns out that these types of oblique triangles can be solved using the law of cosines. So for any triangle A, B, and C, so let me redraw my A, B, C triangle here. So here's A and B and C, and here's little a, little c, and little b. All right, and so for any one of these triangles with our three angles, capital A, B, C, and our three sides, lowercase a, b, and c, right? We have the following three law of cosines. C squared is a squared plus b squared minus 2ab cosine c, and then so forth and so forth and so on. What you'll notice is the formulas are very similar, but the only difference is that the C side, right, which is opposite angle C, right, that is basically, if we have the cosine of angle C, then the C side C squared is isolated, and everything is in terms of A's and B's. If we have the cosine of B, angle B, then it's the side B that's isolated, and then basically everything's in terms of A's and C's. And then last but not least, if we have the cosine of angle A, then the side A is the one isolated, and we get our B squared minus C squared equals, in terms of B and C, excuse me. So there's three routines. It just depends on what angle is involved in the cosine. All right, the angle that's involved in the cosine, its corresponding side is the side that's isolated, and then the other two sides are involved in the formula. So there's the formula, and what I'll do is go ahead and do a proof. My proof's a little bit different than the book, so that's why I kind of want to go through it. It's more algebraic in nature, but we'll bring the cosines in. So let's just say we have a oblique triangle, right? Again, here's A, C, and B, right, with side C and side B and side A. What gets this kick-started is what we do is we form a sectional cut of C, and I do it in such a way where I have right triangles in there. So we could do that for any one of the angles. Of course, for A and B it would be harder, right, because that extension would be out. But the proof is very similar. So once I prove one, we basically have a proof for all the other ones. Because again, we just interchange A, B, and C angles and interchange their sides. And so with this, what I now have, right, let me change colors here, is let's go ahead and label this part here X. All right, which means that, so from here to here is an X length. And then from here to here, well, what's left right there will be C minus X. Okay, and let's go ahead and label this as H, right? Kind of basically our height of our little bisection thing there. That height serves as the height for this right triangle on this side, and for this right triangle on that side. And that's basically what I can use to start building my my equations, because we know for a right triangle I have my Pythagorean theorem. As a matter of fact, you can even see, I should have mentioned that back here, if any one of these angles is 90 degrees, the cosine of 90 is 0, and you're basically looking at our Pythagorean theorem. So that's kind of a quasi proof of that, because it's proof for when we have that. But for this triangle that we have right here, right, looking at the sides, the hypotenuse is b squared, right, and it's supposed to equal the side squared, where that would be h squared plus x squared. So we've got that from that right triangle over there on that side. So the hypotenuse, which is b for this right triangle, right, is side squared plus side squared. And then we also have this right triangle. It's going to be a little more complicated. The hypotenuse is a, right, and then we have a side h squared, and then the other side is c minus x squared. So that's for this other right triangle that we have on the other side. And so right now what I have is kind of an algebraic train wreck, right? But let me go ahead and expand some things out, and then it'll slowly, believe it or not, come together that we have up there. So the first thing I want to kind of gather from this, right, is the fact that we can expand this side out over here, all right? And so if we do this, we get a squared equals h squared. This is basically c minus x times c minus x. So we end up getting c squared minus 2cx and then plus x squared. All right, so let me write that a little nicer. So when we expand that out, that should be a plus sign, by the way, because we're adding minus 2cx plus x squared. All right, so that's what happens when I expand that c minus x part out. All right, and then what I'm going to do is make a replacement now, right? Because we can come over to this equation and I can rewrite this and say that h squared is b squared minus x squared. So I'm going to replace that for that h right there. So when I do that, I get a squared equals b squared minus x squared plus c squared minus 2cx plus x squared. And with that replacement, the x squareds now cancel out, and we're basically left with, at this stage of the game, we're left with a squared equals b squared c squared minus 2cx plus x squared. All right, so far so good, all right, with regard to what we have there. All right, and now what we have to do is we have to get rid, that x squared is not going to be there. So we're really, really close, right? If you take a look at this guy here and this guy here, everything is basically spot on. A's where it's supposed to be, B's where it's supposed to be, C squared is supposed to be. I do have a minus 2 times C, but here I have this x, and here I have a B cosine A. So let's figure that out, right? So if we go back to this right triangle, here's my angle A. And as far as the cosine of that angle is, right, cosine is supposed to be the adjacent over the hypotenuse. And so for this situation, for the angle A, right, the hypotenuse is side B, and the adjacent for this one is x. And so multiplying both sides by b, we end up finding that x is b cosine of a. So I can come down here and make that substitution, and we end up with a squared equals b squared plus c squared minus 2. This x is a b cosine of a, and of course there's that c that was already kind of hanging out there. And so you basically have your proof for that one right there. Very easy to prove, right? For B, we could have just resolved some things and considered things on this side. C, a little tougher. We'd have to expand out and get our right triangle over there. But the work is essentially the same. So we prove one, we kind of have a snapshot of what the other proofs are going to be. So there's the proof of the theorem, and it kind of gives you an idea why the angle A, right, is so important with the isolated side A, and then how b squared and c squared and 2b minus 2bc also plays a role in the algebra that we came up. So good algebra there, some nice substitution tricks that we used, very, very common. All right, so I wanted to do more of an algebraic approach than what the book kind of did. Not that the book's wrong, they have a really good approach as well, but as a class, our algebra skills continually need to be improved, so I thought I'd show it to you guys with kind of an algebraic proof with trigonometry coming in the end when I had to figure out how to rewrite that x. Alrighty, so there you go. Now that we have the formula, of course, now what we need to go do is go use it and apply it, and we'll do that in some videos coming soon.